next topic in our chapter talks about a common ion effect. Again, an application of Le Chatelier's principle. If we add a salt containing an anion, and that's what the little A here is standing for, sodium anion, some last name, which is the conjugate base of the acid, there's the common ion, we see a shift in the position of equilibrium to the left. This causes the pH to be higher than the pH of the acid solution, simply because we're removing hydronium ion. So, just kind of thinking through arrows. If I add a salt who has the same last name as the acid, the original stress is about increasing the A negative. Le Chatelier says we're going to counteract that by shifting away from the stress to use it up. If we shift away from the stress, we'll increase the amount of HA in water, but we will then use excess hydronium. If we shift left, the reactants are now hydronium and A negative. If we remove hydronium, it's not as acidic, therefore pH will increase to show that it's becoming less and less acidic. Remember the pH scale, the lower the numbers, the more acidic it is. So the pH actually begins to rise closer to the 7 neutral point because we're removing hydronium. Common ion effect says if we add in an ion that's already in a solution, we're going to cause that equilibrium to swing. Taking a look at this particular slide, it says suppose we have an acetic acid solution and we have a pH of 2.9. We add a salt, sodium acetate. Notice they have the same last name. The common ion between acetic acid and sodium acetate is the acetate ion. Adding those two together will create a solution that increases the original pH of the acid. 2.9 was the pH of our original acetic acid. 8.9, the original pH of the salt. Add them together and we get 4.7. Removing the hydronium ion increases the pH. Let's show that in terms of an equilibrium. So acetic acid is a weak acid. I'll just show an equilibrium arrow. It's in dynamic equilibrium with hydrogen ion and acetate ion. You can choose to show the water, but I'm going to choose to leave it off and just show the equilibrium between hydrogen and acetate. If I add in sodium acetate, the common ion is the acetate ion. Adding the salt creates an original stress of increasing that concentration. I point away to lower that. Le Chatelier says if you create a stress, you'll do the opposite to relieve the stress. The opposite of more acetate is less, and to use it up, we point away. Now remember, pointing away says we're going to take out some of the hydrogen ion as well, increase the molecular form of the acid. Removing hydrogen ion raises the pH. Not as acidic, and we see the pH climb from 2.9 to 4.7 when they're placed together. What is the pH of a buffer that's 0.1 molar acetic acid and 0.1 molar sodium acetate? The equilibrium is about the weak acid. Now remember, sodium acetate is a strong electrolyte. It's a salt. It 100% dissociates. There's no equilibrium arrow for this particular strong electrolyte. It 100% dissociates. This acetic acid is a weak acid. It does set up an equilibrium, and that's what's shown to us here. The acetic acid, when dissolved in water, will form an equilibrium with its conjugate base and our hydronium ion. Remember, the hydronium is where we take the negative log at the equilibrium to find the pH. We know the original concentration of HA is 0.1. The negative ion, the acetate, comes from the source of the 0.1 sodium acetate. And at this particular point in time, we have no hydronium ion, approximately 0, because it does slightly dissociate, but we'll call it 0. When acetic acid combines with water to form the conjugate pairs hydronium and acetate, we take the original concentration of the acid, the original concentration of the salt, and 0 for the hydronium ion, and we begin to construct an ice chart. It says assuming that the hydronium from water is approximately 0. So we're going to say there's no appreciable dissociation of a water molecule. Alrighty. So if we add salt and we combine those two, to what we're getting here is the common ion. So this here is the common ion in this equilibrium, and that's why I'm putting that down as 0.1 molar, the source of the acetate ion. Alrighty. Now originally the equation is going to occur from left to right, and I'm just kind of peeking ahead. They're showing us from left to right. So if we use up X amount of HA going from left to right, we are going to produce the same amount of the ion, since it's a 1-to-1 stoichiometric ratio. Here we would have 0.1 minus X, 0.1 plus X, and the value of X at equilibrium. Let me turn the page and we'll catch up the ice chart to the second page here. So we've said HA gets used, A negative gets made, and hydronium gets made. Now they're just taking a shortcut. This represents any weak acid. Here's its conjugate base and the hydronium starting at 0. The equilibrium expression, called Ka since it's a weak acid, is products over reactant. Of course, the water drops out because it has no concentration. The acetate ion, 0.1 plus X, times the concentration of hydronium, the value of X, set over 0.1 minus X, the concentration at equilibrium. What we set that equal to is the Ka for acetic acid. That's something that we will have to look up, or it usually is provided in the story problem. The Ka usually is a constant well enough that I know, 1.8 times 10 to the negative fifth, the constant for acetic acid. Flip the page and we'll see the algebra. Finding the value of 1.8 times 10 to the negative fifth, and we subbed in the value of the concentrations at equilibrium, 0.1 minus X for HA, 0.1 plus X